Filter circuits are two-port networks. The signal to be filtered is applied to the input terminals, and only the components in the frequency range of interest appear at the output terminals. The phenomenon of resonance is used to improve the performance of filters in rejecting unwanted signals. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I would like to invite you for a debate about filters and how the phenomenon of resonance boosts their performance in rejecting unwanted signals. Through 13 exercises that frequently appear in exams for electrical engineers. Let's go to the first exercise. Exercise number 1. Given the magnitude and the phase plots of a filter's transfer function, this is the magnitude and this is the phase plot of the transfer function. The question: determine the output signal if the input is Vin is equal to 2 times the cosine of 2000 pi t plus 40 degrees. Okay, my friends, this is the question. Let's go to the solution. The solution: any sinusoid can be modeled as in other words, any sinusoid can be modeled as a function in the time domain having a magnitude, a frequency, and a phase. Comparing the general representation of a sinusoid with the function given, we infer that Wt is equal to 2000 pi t, and that the angular frequency in this case is 2000 pi. We know that W is equal to 2 times pi times f. Consequently, in this case, the frequency in hertz is 1 kilohertz. Now, if we inspect the plots, the magnitude and the phase plots, we observe that for the frequency of 1 kilohertz, the magnitude of the transfer function for the frequency of 1 kilohertz is 3. And the phase. The phase for the frequency of 1 kilohertz is 30 degrees. Then, for the frequency of 1 kilohertz, the transfer function is 3 phase 30 degrees, okay? Which is equal to the division between the output voltage and the input voltage. Okay? As the phasor for the input signal is 2 phase of 40 degrees, Vin is 2 phase 40 degrees volts, we find V out by multiplying the input phasor with the transfer function at 1 kilohertz. Thus, V out is equal to H for 1 kilohertz times the input voltage phasor, and this is 3 phase 30 degrees times 2 phase 40 degrees, and we find that the output voltage phasor is 6 phase 70 degrees. If we convert this to the time domain, the output signal is V out equal to 6 times the cosine of 2000 pi t plus 70 degrees volts. And this is the solution of the exercise using the magnitude and the phase plots of the transfer function. And what is the conclusion that we get? The conclusion is that in this case, the amplitude of the input signal is tripled. It was 2 after passing through the filter. It becomes 6. Furthermore, the signal is shifted by 30 degrees. The phase was 40 degrees, now the phase is 70 degrees, while passing through the filter network. Okay, my friends, this is all for exercise 1. Let's go to exercise 2. Now, let's extend what we learned in exercise 1 to a signal with multiple frequencies. Exercise number 2, for the transfer function of the previous exercise, find an expression for the output signal if the input signal is. Now the input signal is this, a signal with components in different frequencies. Let's go to the solution. We begin by breaking the input signal in its components. Component number 1, the in1 of t is equal to 3. The in 2 of t is equal to 2 times the cosine 2000 pi t. And the third component, the in 3 of t is equal to cosine 4000 pi t minus 70 degrees. If we inspect the magnitude and the phase plots of the transfer function, we find the components for each of the input components. Okay? We are going to find the transfer function, the value of the transfer function for each of the input components. All right? For the first component, the transfer function will be the frequency of the first component is 0. For the frequency of 0 Hertz, the magnitude is 4. Okay? And the angle for 0 Hertz is 0 degrees. Now let's do the same for the second component, whose frequency is 1 kilohertz. The magnitude for 1 kilohertz is 3 and the angle 30 degrees. And lastly, for the frequency of 2 kilohertz, the magnitude is 2 and the frequency is 60 degrees. Okay? Now that we know each of the components and the respective values of the transfer function, we can calculate the output. Let's go step by step. For the first component, the out 1 is equal to the value of the transfer function for the first component, which is 4 phase 0 degrees, times the phasor for the first component, which is 3 phase 0 degrees. And this is equal to 12 phase 0 degrees volts. Likewise, for the second component, the value of the transfer function for the frequency of 1 kilohertz is 3 phase 30 degrees. And the voltage phasor for the first component of the input signal is 2 phase 0 degrees. 2 phase 0 degrees. And this is equal to 6 phase 30 degrees. And lastly, for the third component, for the frequency of 2 kilohertz, the value of the transfer function is 2 phase 60 degrees. And the phasor of the third component of the input signal is 1 phase negative 70 degrees. And this is 2 phase negative 10 degrees. What we need to do now is to convert this to the time domain. And after doing this, the output signal becomes V out of t is equal to 12 plus 6 times the cosine of 2000 pi t plus 30 degrees plus 2 times the cosine of 4000 pi t minus 10 degrees, this all in volts. Okay, my friends? Have you fully comprehended what I did? If not, please leave me a message, okay? And this is all for exercise 2. Let's go to exercise 3. Exercise number 3. Suppose that the following input signal, Vin, with components in different frequencies, is applied to the low-pass RC filter of the figure. Find an expression for the output signal. Okay? This is the exercise. Let's go to the solution. The first step will be to come up with the transfer function of the RC connection. Okay? The output voltage divided by the input voltage is the transfer function H of S in the frequency domain. Okay? And it is equal, in this case, of ZC of S divided by ZC of S plus R. Alright? In the frequency domain, the capacitive impedance is equal to 1 over SC. Alright? But here we are assuming that S is equal to JW. And since W is equal to 2 pi F, we are going to assume that S is equal to J2 pi F. Alright? This is our assumption. This is what we are going to work with. And if we apply this here and this here, we find the transfer function as a function of a frequency, my friends. Okay? The transfer function as a function of frequency is going to be H of F equal to 1 over 1 plus J F FB, where FB is the corner frequency or the half power frequency. The half power frequency, this transfer function here is also represented in the frequency domain. In some textbooks, you also find this transfer function in this way here. Okay, 1 plus j w wb. Okay, we are going to use this, but if you use this and if you are more accustomed to this, your teacher in college taught you using this, it is the same. I am just telling you that there is another way of seeing the problem, and we are going to use this instead here. And FB is equal to 1 over 2 pi RC. Okay, you may have already heard of WB. WB is equal to 1 over RC. Okay, but for us, this is going to be this. We are going to work with this kind of representation, all right? And knowing the values of the resistance and the capacitance, substituting here 1 kilo ohm and here 1.5 microfarad, we find that FB is equal to approximately equal to 100 hertz. Okay, my friends, this is what we are working with, and now we are going to work with the components. We are going to find the output voltage for every one of the components, but separately. Okay, let's go. Let's work on the first component of the input signal first. The first component of the input signal is V in 1 over t equal to 5 times the cosine of 20 pi t, and the corresponding phasor is V in 1 equal to 5 phase 0 degrees volts. Alright, we already know that the angular velocity or the angular frequency is 20 pi, and from this we know that the frequency is 10 hertz. Then for the frequency of 10 hertz, we find that h of f equal to 10 hertz is equal to 1 over 1 plus j 10 over 100. We are using the transfer function that we just calculated, but now we are applying the frequency of 10 hertz, and calculating, we find that the transfer function exclusively for the frequency of 10 hertz is 0.995 in the phase negative 5.71 degrees. Okay, and the output phasor is going to merely be the multiplication between the transfer function and the phasor of the first component of the input signal. And if we multiply, we find that V out is equal to 4.975 in the phase minus 5.71 degrees volts. Okay, my friends, this is the output voltage of the first component. Let's do this same computation for the second component and see what we get. It is easy once you've understood how we do it. It is easy. We are going to repeat the process for the second component. Okay, similarly for the second component, V in 2 of t is equal to 5 times the cosine of 200 pi t. Okay, and the corresponding phasor is V in 2 equal to 5 phase 0 degrees volts. And we know that the angular frequency is 200 pi. If we divide by 2 pi, we find the frequency in hertz, and the frequency in hertz in this case is 100 hertz. And the transfer function in this case for the frequency of 100 hertz, h of the frequency of 100 hertz is equal to 1 over 1 plus j 100 over 100, and this leads to a value of 0.707 in the phase negative 45 degrees. Okay, and similarly as we did before, the output value of the second component of the input voltage will be merely the multiplication between the value of the transfer function by the phasor of the second component. And for us here, V out 2 is equal to 3.535 in the phase negative 45 degrees volts. Okay, easy, isn't it? Now to finish, we do the same for the third component. The value, the third component is V in 3 of t is equal to 5 times the cosine 2000 pi t, which leads to a phasor V in 3 equal to 5 phasor 0 degrees volts. Observe that the phasor is equal for the three components, but the transfer function is different. Why? Because they are in different frequencies, and the transfer function will impact the signal differently depending on the frequency. And we see that here the angular frequency is 2000 pi, which leads to a frequency in hertz equal to 1000 hertz, or if you prefer 1 kilohertz. And if we calculate the transfer function for 1 kilohertz, we find it is 1 over 1 plus j 1000 over 100, and this is equal to 0.0995 in the phase negative 84.29 degrees. Okay, my friends, this is the value of the transfer function exclusively for the frequency of 1 kilohertz. And likewise, as we did before, the output phasor is going to be simply the multiplication between the value of the transfer function and the phasor of the third component of the input voltage. And this is equal to V out 3 equal to 0.4975 in the phase negative 84.29 degrees volts. Okay, now that we have all the output phasors, what we need to do is to convert them, is to translate them to the time domain. And this is the last step of this exercise. We are going to translate, we are going to convert them to the time domain, and they become V out V out of t is equal to 4.975 times the cosine of 20 pi t minus 5.71 degrees plus 3.535 times the cosine of 200 pi t minus 45 degrees plus 0.4975 times the cosine of 2000 pi t minus 84.29 degrees, it all in volts. Okay, my friends, this is the result of exercise 3, and notice the conclusion that we take from this is that the lower the frequency, the less the signal will be attenuated by the filter, okay? They have the same magnitude, but the frequency is different. The, the signal with the frequency of 10 hertz is not much attenuated by the filter, but the signal with the frequency of 1 kilohertz is very much attenuated by the filter. Okay, the 10 hertz component is nearly unaffected, while the 1 kilohertz component is greatly attenuated. This is all for exercise 3. Let's go to exercise 4 now. Exercise number 4. Sketch the body magnitude and phase plots of the following circuit. This is the circuit in which the value of the resistance is 159 ohms and the value of the capacitance 1 microfarad. Okay, my friends, let's go to the solution. As we saw in the previous exercise, the transfer function for the RC connection is H of F is equal to 1 over 1 plus J F over FB. Okay? Where FB is called the resonant frequency or the half power frequency. Some people call it the cutoff frequency as well. Okay? And the magnitude of this transfer function is the magnitude of the transfer function is 1 over the square root of 1 plus 1 over FB squared. The square root of it all. Okay, this is the magnitude, and now the phase. The phase is the negative of the inverse tangent of F over FB. Okay? Where, once more, where FB is the corner frequency or the cutoff frequency. Let's find the value of FB. We know that WB is equal to 1 over RC. Okay? But we are using F instead of W. Then we know also that W is equal to 2 times pi times F. Okay? Dividing this by 2 times pi, we know that FB is equal to 1 over 2 times pi times RC. Okay? If we substitute the values, okay, in the place of R, we put this value, and in the place of C, we put this value, and we find that FB is approximately equal to 1 kilohertz. Okay? FB is here. FB is 1 kilohertz. Now let's work on the body plots. Let's work on the body plots. We are going to use this and this to sketch this, okay? The circuit will act as a low-pass filter, okay? Attenuating frequencies above 1 kilohertz. Observe that the capacitor is connected shunt here, okay? For low frequencies, the signal will pass from input to output. But for high frequencies, the signal will go to ground. The capacitor is going to drain high frequencies to ground. The signal is not going to pass from input to output. And alright, I said it in words. Let's try to understand it with numbers. Okay? For the body plots, we need to convert the magnitude to decibels. The magnitude in decibels is equal to 20 times the logarithm of this magnitude here. Okay? We take this value here, we take the logarithm of it, and then we multiply by 20, and we have the value in decibels. For the frequency of 100 hertz, the value in decibels is going to be approximately equal to 0. Okay? How do we do it? We take the value of the frequency and we put here. And we divide by the value of the half power frequency, or if you prefer, the cutoff frequency. And we square the value, add 1, we take the square root of it, 1 over it is the value in number, okay? If we want in decibels, we take this value, we take the logarithm of this value that we just found, and multiply by 20, and we find for the frequency of 100 Hz 0. Likewise, for the frequency of 1 kilohertz, the magnitude in decibels is equal to negative 3 decibels. Okay? Pay attention on this. Okay? Pay attention on this. We are going to return to it later, but pay attention on this. For the frequency of 10 kilohertz, 10 kilohertz, the magnitude in decibels is equal to negative 20. And similarly, for the frequency of 100 kilohertz, the magnitude in decibels is equal to negative 40. Okay? With these values here, we can construct this graph, okay? This plot. But observe that here, for the frequency of 100 Hz, the magnitude is 0. Let's jump this and understand this first. For the frequency of 10 kilohertz, the magnitude is negative 20. Negative 20, 10 kilohertz. For the frequency of 100 kilohertz, the magnitude in decibels is negative 40 decibels. Negative 40 corresponding to 100 kilohertz. But we have here negative 3. Here it is 0 at 1 kilohertz, and we've found 3 decibels here, negative 3 decibels. Why the difference? The difference is that this is an approximation. This straight line graph here is an approximation, okay? The actual graph, the actual plot, is something of the sort. All right? And there is a deviation or an error of 3 decibels from the actual graph to this straight line approximation here that we frequently work with. Okay? So there is this deviation here, or this error of 3 decibels at the cutoff frequency, okay? Which in this case is 1 kilohertz. Now let's work with the phase. The phase. We worked with the magnitude in decibels, let's work with the phase. We do not work with the phase in decibels, okay? We work with the phase in the angle, okay? In degrees here. We use this. The phase is the negative of the inverse tangent of the frequency divided by the cutoff frequency. And for the frequency of 100 Hertz, the angle, if we put it here, 100 here, and the the knee frequency or the cutoff frequency is 1 kilohertz. If we divide and take the inverse tangent of it, we find that for the frequency of 100 hertz, the angle is equal to negative 5.7 degrees. Okay? For the frequency of 1 kilohertz, using 1 kilohertz here and 1 kilohertz here and taking the inverse tangent, we find that the angle is negative 45 degrees. And for the frequency of f equal to 10 kilohertz, the angle is negative 84.3 degrees. And for the frequency of 100 kilohertz, the angle is negative 89.5 degrees. Okay? And similarly, as we saw for the magnitude, there is a deviation from this straight line approximation to the actual curve. Okay? Here, there is going to be a bending here. Okay? The curve is going to bend here and is going to bend here as well. Okay? And the difference here and here from the actual curve to the straight line approximation is this angle here, 5.7 degrees, and here 5.7 degrees. Okay? At the moment the curve leaves the x-axis, that is this deviation of 5.7 degrees. Okay? Here and here. All right? If you do this for the frequency of 10 kilohertz, 90 degrees minus 84.3 degrees, we get 5.7 degrees. Okay? So that is this deviation. We assumed here 90 degrees, but in reality it is 84.3 degrees. Okay? And this is all for exercise 4. Let's go now, my friends, to exercise 5. Exercise number 5. Determine the corner frequency of a first order high pass filter that has a transfer function magnitude of negative 30 decibels at the frequency of 60 hertz. Okay, the exercise said that the magnitude of the transfer function is negative 30 decibels at the frequency of 60 hertz. Okay? And the exercise wants us to determine the corner frequency. Let's do it. Let's solve this exercise. The magnitude of the transfer function of a high-pass filter can be described in terms of frequency as, okay? For a high-pass filter, the magnitude of the transfer function can be described as f over fb, 1 plus f over fb squared and the square root of this all. Okay? However, for frequencies much lower than the corner frequency, the following approximation is true. Okay? This is the approximation that we are going to take to solve this exercise. You can check this in a reference textbook of electronics, and you're gonna discover that for F much lower than FB, this holds true. The magnitude of the transfer function in decibels is approximately equal to 20 times the logarithm of F over FB. Okay? Simple as that. With this expression, we can use the values provided by the exercise. Therefore, 20 times the logarithm of F over FB will be equal to negative 30 decibels. Okay? And for the frequency of 60 hertz. 60 hertz. We are going to use here 60 hertz. And if we pass dividing 20 dividing negative 30, we know that 1.5 is equal to the logarithm of 60 divided by FB. Okay? And from this we know that 10, because here it's the logarithm in the base 10. 10 raised to the power of negative 1.5 is equal to 60 over FB, and hence FB is equal to approximately equal to 1.9 kilohertz. Okay? Observe that in this case it holds true because we are assuming that the frequency given is much lower than the knee frequency or the corner frequency. See that 1.9 kilohertz is much greater than 60 hertz. Then this approximation here holds true. Okay, you can check this in a reference textbook. Okay, it is easy to come up with this expression here, all right, for a high pass filter, but this approximation here can only be found in a reference textbook. People that have experience, they know that it is going to be difficult to work with this, and they discover that there is a better way of working with this kind of problem, and they use this approximation here. Okay, and this is all for exercise 5. Let's go to exercise 6. Exercise number 6. Consider the series resonant circuit of the figure. Letter A. Compute the resonant frequency, the bandwidth, and the half power frequencies. Letter B. To model a bandpass filter, assume that the frequency of the source is the same as the resonant frequency, which represents the signal that shall pass unordered. In this case, find the voltage phasor across the elements and draw a phasor diagram. This is the exercise, my friends. Let's go to the solution. Observe that along the path of current, the equivalent impedance is this, okay? For low frequencies approximately equal to 0, For low frequencies, the capacitive reactance is large. Okay? The capacitive reactance is large for low frequencies. And for very high frequencies, going to infinity, the inductive reactance is large. Okay? The inductive reactance is large for high frequencies, and the capacitive reactance is large for low frequencies. The resonant frequency reduces the circuit's impedance to a minimum, and it occurs when the impedance is purely resistive. When the equivalent impedance is purely resistive, we have that the resonant frequency is equal to 1 over 2 pi times the square root of LC. Okay? Only at the resonant frequency, the equivalent impedance is purely resistive. Okay? And we are going to find this resonant frequency using the values of L and C here. Okay, we find that the resonant frequency is approximately equal to 1 kilohertz. Okay? This is our first result. Now let's calculate the quality factor. The quality factor represents the degree to which the system is underdamped, or how much it resonates. The quality factor is equal to WO times L over R, which is equal to 2 times pi times FO times L divided by R, and this is equal to 10. Okay? If we use the values of FO, L, and R, we already know them. FO is this, L is this, and R is this. Then we find the quality factor equal to 10. As the bandwidth is the measure of how narrow or wide is the band of frequencies that will pass, it depends on the quality factor. Observe that the larger the quality factor, the narrower the bandwidth for a given frequency. Okay? Sometimes we wish the bandwidth to be the narrowest possible, as in notch filters. Okay? Then they are correlated in this way. The bandwidth is correlated to the quality factor in this way here. Okay? We use the values here. FO is 1 kilohertz and the quality factor is equal to 10, and we find our bandwidth as 100 hertz wide. Okay, our bandwidth is 100 hertz wide. All right, as Q is sufficiently greater than 1, okay, is 10, as the quality factor is sufficiently greater than 1, the following approximations hold true. Okay, you can find these approximations in your favorite reference textbook, and you're gonna see that FH is equal to FO plus B over 2, and FL is equal to FO minus B over 2. Okay, these are the half power frequencies. Okay, we have something of the sort here. Okay, and here we have FH, and here we have FL, and they represent the half power frequencies. All right, and their value are, if we use the values of B here and here and of FO, we find that FH is 1050 hertz and FL 950 Hertz. Okay? These are the half power frequencies. And now let's calculate at resonance. At resonance, let's calculate the impedances, the capacitive impedance and the inductive impedance. The inductive impedance is J2 pi FOL at resonance, which is equal to J1K ohms. Okay, you just use the values. We already calculated this, and the exercise gave the value of the inductance. And the capacitive impedance is negative J1 over 2 pi FOC, and this is equal to negative J1 kilo ohms. All right, you see that when put together they cancel each other out. As expected, the reactances are equal in magnitude at the resonant frequency, but of opposite signs. Then at resonance, Z of S, okay, the equivalent impedance is R plus ZL plus ZC, which is equal to 100 ohms plus J1 kilo ohms minus J1 kilo ohms, and this is equal to 100 ohms. Okay? Now let's go to letter B. Letter B. This is all for letter A. Let's go to letter B. At a frequency equal to the resonant frequency, 1 kilohertz, the current will be equal to V in divided by Z. But Z, we have already calculated that at the resonant frequency, the equivalent impedance is equal to the value of the resistance. And this is then equal to 1 phase 0 degrees divided by 100 ohms. And this gives a current of 0.01 phase 0 degrees amps. Okay? The voltages across all the elements can be calculated using the current. VR is equal to R times I, and this is equal to 100 ohms times the current, 0.01 phase 0 degrees, and this is a voltage of 1 phase 0 degrees volts. Likewise, we calculate for the inductance. It is going to be 1000 phase 90 degrees multiplying the current 0 degrees, and this is 10 phase 90 degrees. And for the capacitor, it is 1000 phase negative 90 degrees times the current, and this is 10 phase negative 90 degrees. All right, now we have the values of the voltages, and we can chart them, okay, in this way here. This is VL, this is VC, and this is VR. Okay? Observe that although the voltages across the inductor and the capacitor are 10 times larger than the voltage of the source, KVL is satisfied because VL and VC cancel each other out. Alright, my friends, this is all for exercise 6. Let's go to exercise 7. Exercise number 7 now. Find the values of C and L for a parallel resonant circuit that has R equal to 10 kilo ohms, the bandwidth equal to 100 kilohertz, and the resonant frequency equal to 1 megahertz. And if the current of the source is 1 phase 0 degrees milliamps, draw the phasor diagram showing the currents through each of the elements at resonance. Okay, my friends, this is the question. Let's go to the solution. We are going to work on a parallel resonant circuit of this sort. Okay, this is the parallel resonant circuit. To compute the values of C and L, we will use the quadratic factor and the bandwidth. Okay, we need to use the quadratic factor and the bandwidth. If we consult a reference textbook, we find that the value of the inductance is equal to R over 2 pi FO times the quadratic factor. Okay, and similarly, we find that the capacitance is equal to Q over 2 pi FO times R. The relationship between Q and B, the quadratic factor and the bandwidth, is Q is equal to FO over B. Okay? And substituting the values, we find that Q is equal to 1 megahertz, 10 to the 6th, divided by 100 kilohertz, which is 10 to the 5th, and this is equal to 10. Okay? We can find now the inductance and the capacitance because we already have Q. All right, let's find it. L is going to be equal to the value of the resistance, which is 10 to the 4th ohms, divided by 2 times pi times the resonant frequency, which is 10 to the 6th hertz, times 10, which is the quadratic factor, and we find a value of 152.2 microhenry. For the capacitor, we find that Q is equal to 10 divided by 2 times pi times the resonant frequency, 1 megahertz, which is 10 to the 6th hertz, times the resistance, and the resistance is 10 kilo ohms. And this gives a value of capacitance equal to 152.2 picofarad. All right? These are the values of the inductance and the capacitance when the quality factor is 10, which means that the resonant frequency is 10 times the bandwidth. And in this case, the bandwidth is 100 kilohertz and the resonant frequency is 1 megahertz. And in this case, both the inductance and the capacitance are dependent on the value of the resistance as well. Okay? For this resistance here, and this bandwidth and this resonant frequency, the value of the inductance and the capacitance are these. Alright, at resonance the output voltage is given by, alright, the output voltage V out is equal to I times R. At resonance, the parallel connection between the inductor and the capacitor will act as an open circuit, okay? ZC in parallel with ZL is equal to infinity. They work as an open circuit together, and all the current of the source will pass through the resistor. But they are in resonance, okay? It doesn't mean that the currents here and here are zero. No, not at all. Not at all. There will be current here and current here. They work as if they represent an open circuit, but in reality it is not the case. They are in resonance, and they behave as an open circuit, but there is going to be current here, and IL plus IC is equal to 0, okay? The currents are the negative or the opposite of each other. This is the conclusion that we are going to take when we finish the problem. In this case here, knowing this, we know that the output voltage V out is going to be equal to I, which is 10 to the negative 3 phase 0 degrees amps, times the resistance, which is 10 kilo ohms, 10 to the 4th ohms, and this is equal to 10 phase 0 degrees volts. Okay? This is the output voltage. 10 phase 0 degrees volts. Alright? To finish, let's calculate the currents. The exercise wants us to calculate the currents here, here, and here. We already know that the current through the resistor is this, the current of the source, 1 milliamps, because they are in the inductor is in resonance with the capacitor, okay? And let's calculate it. Enough of words, let's calculate. I want to see it in numbers. Let's do the math. IR is equal to V out over R, which is equal to 10 phase 0 degrees divided by 10 kilo ohms, 10 to the fourth ohms, and this is equal to 10 to the negative 3 phase 0 degrees amps, or if you prefer, 1 phase 0 degrees milliamps, which is precisely the current of the source. Let's calculate the inductor and the capacitor currents. IL is equal to V out over ZL. But ZL, the inductive impedance, or if you prefer the inductive reactance, is 10 phase 0 degrees divided by J 10 cubic. And this is 10 to the negative 2 phase negative 90 degrees amperes, or if you prefer, 10 phase negative 90 degrees milliamps. Likewise, for the capacitor, we do this. IC is equal to V out over negative J over 2 times pi F0C, which is equal to 10 phase 0 degrees over negative J10 cubed, which is 10 to the negative 2 phase 90 degrees, positive now, amps, which is 10 phase 90 degrees milliamps. Okay? These are the currents. These are the current phasors. And the exercise wanted us to draw the phasor diagram showing the currents. Okay? The phasor diagram is going to be this. Okay? This is IC, this is IL, and this is IR. Alright? Notice that both the inductor and the capacitor currents are larger in magnitude than the current of the source at resonance. Okay? They are 10 times the current of the source. However, as they cancel each other out, it is obvious here, okay, that IL plus IC is equal to 0. Observe that as they cancel each other out, KCL is satisfied. Alright? And my friends, this is all for exercise 7. Let's go to exercise 8. Exercise 8. Design a second order high-pass filter that passes components higher in frequency than 1 kHz and rejects lower frequencies. Calculate C and R if L is 50 millihenry, L is 50 millihenry. For this value of inductance, calculate C and R. and the requirement is that frequencies higher than 1 kilohertz shall pass, and frequencies lower than this shall be rejected. Okay, my friends, this is question 8. Let's go to the solution. As capacitors allow high frequencies, okay, capacitors work as short circuits for high frequencies, and while inductors act as open circuits for high frequencies, the capacitor will be in series and the inductor will be in shunt. Okay? This is the configuration of the second order high pass filter that the exercise wanted us to design. Note, observe that the higher the value of Q, okay, you can find this graph in a reference textbook. Observe that the higher the value of Q, the quality factor, larger will be the peak of the transfer function at the corner frequency. The corner frequency or the resonant frequency is this. The higher the value of the quality factor, larger will be the peak at the corner frequency. We want the transfer function to be approximately flat in the pass band. Okay? So we choose a Q. We choose a Q equal to 1 and a cutoff frequency or resonant frequency equal to 1 kilohertz. Okay, this is our design. And since FO, the new frequency or cutoff frequency is 1 over 2 times pi times the square root of LC, you may have already learned this in this way. WO equal to 1 over the square root of LC. But we are not going to work with the angular frequency. We are going to work with the frequency in hertz. Okay? Let's learn how to do it in this way. It is just a little bit different than what you may have learned in college. And from this, we can calculate the capacitance in this way. 1 over 2 times pi squared times the frequency squared times the inductance. We were given the value of the inductance. Then, knowing this and this, we can promptly calculate the capacitance, just substitute the values. You can put it in your calculator, 2 times pi squared times 1 kilohertz squared times 50 millihenry, okay? And if you use the values, you're going to find that the value of the capacitance is 0.507 microfarad. Likewise, since Q is equal to 2 times pi times FO times L divided by R. You can calculate the value of the resistance using this expression. R is equal to 2 times pi times FO times L divided by Q. We know the value of Q, 1, L is 50 millihenry, FO is 1 kilohertz. Use your calculator and you can find that the resistance is 314.1 ohms, okay? Therefore, to allow frequencies greater than 1 kilohertz and reject lower frequencies, we must use the following values of the resistance, inductance, and capacitance. The resistance is 314.1 ohms. The capacitance is this, which can also be written as 507 nanofarad. And the inductor, the value of the inductance of the inductor is 50 millihenry. Okay, my friends? But bear in mind that you will need to refer to a reference textbook to find these expressions here, okay? You will need to do this, all right? Don't only trust me, trust your favorite book and you will find these expressions as well. All right, my friends, this is all for exercise 8. Let's go to exercise 9. Exercise 9. The circuit shown is to be used as a filter. The cutoff frequency for each RC pair is 318 Hz. Classify this filtering network in which R1 is equal to R2 equal to 10 kilo ohms and C1 is equal to C2 equal to 50 nanofarad. The solution, as capacitors behave as short circuits to high frequencies, the shunt connected capacitor C1 will drain to ground the high frequencies. Thus, R1 and C1 act as a low-pass filter with a cutoff frequency of 318 Hz. Okay? The capacitor will drain to ground high frequencies and will let pass low frequencies. Then this pair here work as a low pass filter. As C2 is in series with the path of signals, it will hold low frequencies and let pass high frequencies. Therefore, C2 and R2 work as high pass filter whose cutoff frequency is also 318 Hz. Okay, the capacitor here will allow high frequencies, okay, and will hold low frequencies. Then this pair here works as a high pass filter. The isolating network prevents R2 and C2 from loading R1 and C1 and backwards signals. The combination R1C1 and R2C2 acts as a band pass filter because all frequencies significantly above and below 318 Hz are attenuated. Okay, my friends, this is all for exercise 9. Let's go to exercise 10. Exercise 10, a voltage of 40 sine 100t is applied at the input terminals of the filter. What is the amplitude of the output signal? Okay, my friends, this is question 10. Let's go to the solution. The frequency of the input signal is the frequency the angular frequency or the angular velocity is 100 radians per second, and since W is equal to 2 times pi times F, the frequency in hertz is approximately equal to 15.9 hertz. Okay? The RC circuit works as a low-pass filter, draining high frequencies to ground through the capacitor. The cutoff frequency is, okay, the cutoff frequency WO is equal to 1 over RC. And this is going to be equal to, we simply use the values, 50 ohms times 200 times 10 to the negative 6 farad. And this is equal to 100 radians per second, which translates to a frequency of approximately 15.9 hertz. Okay? The cutoff frequency or the resonant frequency, okay, resonant frequency when there is both together, inductor and capacitor. But in this case here, the half power frequency or the cutoff frequency is 15.9 hertz. As you can see, the input signal is precisely at the cutoff frequency. Okay, this is the cutoff frequency, and the frequency of the input signal applied is precisely at the cutoff frequency. Additionally, the cutoff frequency, also known as the half power point, is that in which it's the half power point. Okay, then what does it mean? It means that V out times I out is equal to P out. But since it is the half power point, it is going to be half of P in, of the input power, in which V out is equal to V in divided by the square root of 2, and I out is equal to I in divided by the square root of 2. Okay? Why? Why? Here here. P in is equal to V in times I in. Okay? But we want this divided by 2 because we are working at the half power point, which is the frequency of 15.9 hertz. Okay, we calculated it here. Then, for this to be equal to 2, then here is the square root and here is the square root. Alright? Then this is this and this is this. Okay? Have you guys fully comprehended what I said there? In this case, V out is equal to 40 volts divided by the square root of 2, and this is 28.3 volts. And this is what the exercise wanted. The exercise wanted the amplitude of the output signal, and the amplitude is 28.3 volts. Okay, my friends, this is all for exercise 10. Let's go to exercise 11. Exercise 11. The circuit of the figure has a resonant frequency of 577 radians per second. The bandwidth is 6.66 radians per second. Calculate the capacitance if the resistance is 1 kilo ohms. Okay? We are required to calculate the value of the capacitance if the resistance is 1 kilo ohms, the resonant frequency is 577 radians per second, and the bandwidth 6.66 radians per second. Okay? For the parallel connection, or LC parallel connection, the bandwidth is B equal to W0 over Q. Or, depending on the textbook that you choose to use as a reference, B will be equal to FO over Q. Alright? And where FO, WO is equal to 2 pi FO. Alright? We are going to use this instead. Alright? As the values were given in radians per second rather than hertz, we are going to use this instead of this, okay? And the value of the quadratic factor is therefore Q is equal to W0 or WO divided by B, and this is equal to 577 radians per second divided by 6.66 radians per second, and this is equal to 86.64. Alright? We can use the value of the quadratic factor to calculate the capacitance in this fashion. Q is equal to WO RC, where C is equal to Q over WO times R, and using the values, okay, 86.64 divided by 577 radians per second, 1 kilohertz, we find a value for the capacitance equal to 150 microfarads. Okay? This is how we calculate the value of the capacitance using these values provided by the exercise. And this is all for exercise 11. Let's go to exercise 12. Exercise 12. What is the resonant frequency of the circuit shown? We want to find the resonant frequency of this circuit. Okay? Let's try to solve it. For the series RLC circuit, the resonant frequency occurs when the equivalent impedance is purely resistive. What does it mean? Take a look at this. Z of S is equal to R plus SL plus 1 over SC. Okay, this is the equivalent impedance in the frequency domain. Okay, this is the impedance seen by the source. We are grouping the resistance with the inductive impedance, or if you prefer, inductive reactance, and the capacitive impedance, or if you prefer, capacitive reactance. Okay? For S equal to JW, the resonant frequency occurs when R plus JWL plus 1 over JWC is equal to R. The resonant frequency occurs when the equivalent impedance is purely resistive. Okay? If this is equal to this, then we can pass this to this and this becomes 0. Okay? This becomes 0. When this plus this is equal to 0, the frequency is 1 over the square root of LC. But since W is equal to 2 pi f, the resonant frequency can be written as okay? We are going to work with this symbology. Using the values, FO is equal to 1 over 2 times pi times the square root, the value of the inductance, 2 Henry, times the value of the capacitance, which is 1.5 microfarad. You use your calculator and then you find the frequency of 91.8 hertz approximately. Okay? And this is what the exercise wanted us to calculate, the resonant frequency of this circuit if the value of the resistance, capacitance, and inductance are these. Alright? And it is all for exercise 12. Let's go to the last. Let's go to exercise 13. Let's go to the last, exercise 13. For the circuit of the figure, what is the value of C for unit power factor? And the exercises say that the value of the resistance is 100 ohms, the value of the inductance 50 millihenry, and the input signal is 100 sine 377 t. Let's go to the solution. The circuit has unit power factor only when it is purely resistive. That is, as we saw in exercise 12, C of S is equal to R plus SL plus 1 over SC. Okay? This is the equivalent impedance. And we wish the power factor to be equal to 1. When will it happen? It will happen only when the equivalent impedance is purely resistive. But for the equivalent impedance to be purely resistive, provided that S is equal to JW, okay? For this to happen, the frequency has to be equal to 1 over the square root of LC. Okay? And rearranging these, we find that the capacitance is equal to 1 over WO squared times L. Using the values, the capacitance is equal to 1 over 377 radians per second squared times the value of the inductance, 50 millihenry. And the value of the capacitance is 140.7 microfarad. Okay? This capacitor, pay attention, this capacitor, 140.7 microfarad, will resonate with this inductor, 50 millihenry, precisely at the frequency of the power source, at the frequency of the power supply, which is 377 radians per second, okay? This is the frequency of the power supply, 377 radians per second, the angular frequency of the power supply. We wished this. We wanted then the capacitor and the inductor to resonate precisely at the frequency of the power supply. When it happens, they act as a short circuit. They cancel each other out. They cancel their effects. And the equivalent impedance becomes purely resistive. Okay, my friends, this is all for exercise 13. And this is the video that I wanted to make. I hope you learned from it and enjoyed it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye.